Yeah, so I'm going to talk about machine learning today. And okay, cool. So yeah, I'm going to talk about machine learning. As a fun case study, I've turned on these little captions that Google Slides will do for you, just in case anybody has some sort of auditory impairment. Hopefully you can see those. And if not, then I sincerely apologize. So my first question for you today is, have you ever applied for a credit card? I know I have. A few months ago, I went online and was trying to get a credit card, and it had this form where I had to enter a bunch of really personal information. And then at some point, I clicked a button that said submit, and the page loaded. And while that page loaded, apparently they were able to make a decision because it told me whether or not I got this card immediately. And this kind of blew my mind because, first of all, it's crazy that they were able to make this decision so quickly. And second of all, like, I was signing up at 2 a.m. because apparently my idea of a good time, like all my friends are out clubbing, right? Because I guess that's what cool people do. But I was home like trying to churn credit card rewards because that's my idea of a good time. So it's 2 a.m. Why are, like, there can't be humans sitting here grading these things. And even if there were, how could they do it so quickly? And the secret here lies in machine learning. In other words, they're able to use past information to determine whether or not I was a good candidate for this credit card. That's kind of what we're going to be talking about today. Before I get into all of that, I work for a company called Indeed. My name is Samuel Taylor. In every single Indeed presentation, I think you're legally required to have this slide that says we help people get jobs. If you are interested in helping people get jobs, please come talk to me afterward. We love data stuff, and we love talking to data people. There are many things that this talk is and that it aspires to be. Chief among them is to introduce people to machine learning. So if you aren't familiar with it, you are in exactly the right place, and I'm so glad that you're here. It aims to be very friendly to people who are new to this. So even if you're familiar with programming and data and stuff, if you have no idea what machine learning is, you will be fine here. Don't worry about it. At the same time, I hope that this is in some way helpful to people who have more experience. I always find it enjoyable to see what other people have worked on and try to understand the problems that they ran into. And so I hope that in that way, if you do have a little bit more experience, this will be helpful for you. The talk focuses on application because I have found it more interesting to hear about applications of machine learning than to hear about the theory over and over again. At the same time, I try to respect the theory that underlies all these things because it is really, really well thought through, and there's been a lot of research into it, and it can make us better practitioners. There's a lot of things that this talk isn't. The gist is it's not a comprehensive tutorial today. Like, we only have 45 minutes, maybe 40, who knows. So if there's other things that you want to talk about, I'm happy to chat with you afterward, but we're just going to go with a sort of overview today. This is the way we're going to be doing that. We'll first talk about just what even is machine learning, and then the bulk of the talk is going to be these use cases, where in each one we're going to learn something new about machine learning and about what happens when we try to do that in the real world. Let's start by talking about what machine learning even is. So for those of you gathered in the audience today, if you've ever heard the phrase machine learning before, can I get you to raise a hand? Okay, there's some of you who are lying because I've already said it today, and I'm going to keep an eye on you because I can tell. I know which ones of you are crafty. Okay, for those of you who just raised your hand, that's great. If you have used machine learning, definitely like in production, but even if it's just like a cool project that you did on the weekend or something that you thought was really interesting, could you also raise a hand? Okay, cool, awesome, glad you're here. For those of you who didn't raise your hand for that, I'm so glad you're here, and there's going to be a lot of learning. So for those of you who did raise your hands, hopefully there's some new stuff in here for you too. When I first waded into this world, it felt like I was trying to ride the subway in a foreign city. And I would ask for directions, and people would say, oh, well, obviously you just do this and this and this. And it felt like someone was saying, well, just take the purple line to the yellow line and then get off at this stop. I don't know what these things are or what directions I should be going. How could I possibly know this? So to try to make this a little bit more concrete and not so scary, people will break down machine learning into a bunch of different areas. And that's what I've drawn up here on the board today. There are a bunch of different things that we could talk about. This is the way that a lot of people find useful to break things down into. So there's supervised machine learning, unsupervised machine learning, and then there's a whole lot of other stuff. Today we're mostly going to be talking about supervised learning. And this primarily breaks down into classification problems and regression problems. In classification problems, we have some input data and some output data. Here, the input data is yellow. So we have someone's age and their net worth, and then the output data is in purple or pink, I guess, depending on if I'm colorblind. What we see here is we're trying to predict from this input data what is the value for the output data here. And we could draw this on a graph and look at it this way. It's just a convenient way to look at it. And what we're doing when we're trying to do machine learning, for all of the hype and excitement and seemingly magical claims that people make about machine learning, the real thing that happens is we just draw a line. Like, that's the whole magic, is we just figure out a really good way to draw lines, and that solves a lot of problems, as it turns out. So machine learning is kind of this project to get really good at drawing lines. And sometimes these lines are a little squiggly, but they're still lines, you know. So what we could do is, after we draw this line, then ask a question about, okay, this new person comes in, they are this old, they have this net worth, should we give them a credit card? So that's an example that sort of harkens back to this intro idea of, should we give a person a credit card? And this is a way we could teach a computer to do that. As an aside, this is obviously just like a fake example that I drew. In particular, you might notice this very rich 12-and-a-half-year-old who has like $500,000. That's a 1%er right there. Anyway, so then because this point that we're asking about is above this line, we can now say, yeah, we would probably give this person a credit card. Regression is another kind of supervised learning problem where we still have inputs and outputs. In this case, I've drawn the graph a little bit differently. We have our input along the x-axis, and that's the net worth. So given somebody's net worth, how big of a credit limit do we want to give them? And maybe we want to give people with a large net worth more credit because we think they're more likely to pay it back. And we could look at this data that we have in the past, say, you know, we did have a bunch of humans in the room, and they did see, you know, they did actually do these reviews of people and did make a good decision about what size of loan they were going to give someone. And that's the data that we have drawn up here. And then, for all the hype and all the magic, you just draw another line. So that's kind of what machine learning is, and that's great, and that's awful, and that's just what it is. So then what happens is, after we've learned this model, when a new customer comes in, we can put wherever they are on the input data, in this case on the x-axis. We can say this new customer coming in has a $500,000 net worth. We can jog up to the line we drew, and then jog over to the y-axis and say we're going to give this customer a $60,000 line of credit. So those are both examples of supervised learning. Let's now talk about unsupervised learning. So the main algorithm that I think is interesting or good to know when we talk about unsupervised learning is clustering. And what's kind of interesting in unsupervised applications is we want to know something about the data, but we're not sure what. So here, we might have these 9 data points, these 9 different shapes, and they have a different number of sides, and they have different colors. And we might tell the computer, hey, can you turn these data points I have into 3 different groups? And the computer can say, yeah, totally, here's a group. Like, I grouped them by color. And you're like, thank you, computer, that's great. But there's no reason the computer couldn't have given you back these groups instead, grouped by shape. So clustering is a way that we try to find some underlying structure in the data without having an explicit output. Whereas in supervised learning, we had either a number or we had we had how much credit did we want to give somebody. That's a good example of a number. Or we have a sort of binary yes/no decision, and that's an example of classification. Whereas in clustering, we don't have that. We just have data, and we want to get some structure out of it. There's a lot of other stuff that is machine learning. This kind of looks like it's a PowerPoint slide. In secret, it's actually an insurance policy against people yelling at me on Twitter. So if your favorite algorithm is not covered, it is. It's right here on this slide. To summarize, machine learning uses data to come up with some approximation for a function that we care about. The goal of machine learning, the thing we really want to do, is find this f of x, this function, this magical function that takes input and produces the exact output. So we could take in the past stock prices and predict the future. That'd be amazing. That'd be the coolest thing ever. We can make so much money. But the problem is that we don't know what happens in those situations. We don't know how this function works. The stock market is very crazy, and there's a lot of factors that go into it. There's so many different players in it. There are so many different factors that come into this that it might even not be possible to know what moves the stock market. The nice thing is that we can measure points drawn from this f of x. We can look at past examples from history and say, we see that when this happens, then this next thing is likely to happen. So when someone releases that they missed their quarterly earnings, the stock will probably go down, something like that. The problem is there's some noise in there, but it can give us hope that we do have some information, some signal in there as well. So to summarize, the way that I think about machine learning is it is a set of algorithms in which you try to find some function g of x that approximates f of x reasonably well. Let us now begin with our first use case of the day. All of these use cases are going to go through these 5 questions. The first question is going to be, what is the problem? In this case, the question is, should we, the bank, give this consumer a credit card? So a consumer comes to us and we want to know whether we should give them a credit card. The data looks something like this. This is the same data I showed you before. I just figured out how to use Google Slides better and made a prettier table. So we have some data, we have age and net worth, and then we know whether or not this person was given credit. Here's my favorite part, and it will soon be your favorite part of each of these use cases, is the question, what kind of machine learning problem is this? So this is the audience participation part. Does this sound like a classification problem, a regression problem, a clustering problem, something else? Shout at me. Get your anger out. Classification, does anybody disagree? Anybody think it's something other than classification? Seeing some head shake. Yes, y'all are very astute. Great work. Yes, this is a classification problem. The solution here, we are at a PyData conference. The solution is Python and scikit-learn. It's going to be great. And it's surprisingly simple to do something like this. We can import this linear classifier from scikit-learn and then set up our data. I have it drawn up here in that same graph that we had earlier just to represent that this data here is just trying to represent the stuff we had on the graph. We can instantiate the classifier object, call fit, and fit is that step where we draw the line in the first place. So by calling fit, we come up with some line that separates these two classes. And then when a new person comes in, who is 63 years old and has $500,000, we can figure out whether or not the model says we should give them credit by calling this predict method. And that's where I have this question mark. That new person came in, and the model will output whether or not we should give them credit. And in this case, we should. When I do this, my first question is this good? Like, should I use this model? How accurate is it? Like, can I use this? And this is where we get into some tricky things with machine learning about measuring error. This is not a trick question. Who thinks that model A, this blue line that I have that's sloping down and to the right, who thinks that model A is doing a better job at approximating these points than model B is? Does anybody think? Okay, good. I warned you. It was a trick question. Yeah, model B is definitely better. If we look at this true function, this actual f of x, which is this green line that I drew, we can see that the blue line on the right is a lot closer to that line than model A is. And that's easy for us to see as human beings. We can see, oh, these lines are pretty close to each other. That's good. But we have 2 things confounding us here. First of all, in real life, we don't know where the green line is. We don't know the true function that underlies all of this. The second thing that's tricky is that we have to come up with some way of quantifying the amount of error here. We can look at these lines and say they're close, but how do we tell a computer to figure out how close 2 lines are? The basic thing that we should do here is to randomly split our data up into training data and testing data. And there is, the gist here is that if we had a bunch of data, we could randomly say, 20% of it, let's not look at it. Let's train the model on the other 80%, and then we can evaluate it on the testing data. So there's, again, a great scikit-learn method called train test split that you can use to do this. And then we can train a model. So what I did here, let me explain this graph a little bit. What I did here was took the data that's on the left, trained a model on it, and then the sort of regions that are colored in are the predictions from the model. So the model thinks that this blue region is the area where all the blue points live. And it's wrong in some cases. Like it doesn't realize that there should be some blue points up here. Even in the training data, it wasn't able to perfectly get this function correct. And there's a little orange point over here that it also did not correctly identify. And that'll happen. But the interesting thing here is that because we set the testing data aside and because we separated it completely at random, we can now take the same colored regions, overlay them on our graph of the testing data, and then count up how many errors it makes. So we see, in this case, it makes 2 errors out of 20 points. And so we might think that, okay, in the real world, when we're doing this, because on our testing data, it made 2 out of 20 errors, we might think that our model is going to be wrong in 10% of the cases. And that's a way we can get a sense for how good our model is. Ideally, at this point, what you would do is calculate the actual cost of something bad going wrong. And what I mean by that is if we were trying to build a system that took in radar data and tried to determine whether a nuclear warhead was coming at the US. And we're wrong. Like, there's not actually a nuclear warhead. Everyone's going to die because we're going to shoot our nukes, and then everyone's going to shoot nukes, and everyone's going to die. And that's going to be the destruction of the human race is the worst thing that we can imagine happening, right? And the same goes for if a warhead's actually coming to us and we don't see it. Like, there's no chance for us to shoot it down. A bunch of people die. It's really bad. So there's real world costs there. But not every problem is like this. Think about me fingerprinting into my phone. If somebody, if like I'm trying to get into my phone and it rejects my fingerprint, I get a little bit annoyed, but I just tap it again, and then it realizes it on the second chance. And so rejecting me that first time was fine. Like, it's a little bit annoying, but it's a lot better than somebody who's not me being able to get into my phone. So if that happens, someone's able to fingerprint into my phone, they can look through my memes and tell me that they're not funny, and that's going to hurt my feelings deeply. I'm going to have to go get some therapy after that, and that's like, those people are expensive. It's like $80 an hour. So there's a lot bigger cost there associated. So ideally what we could see is, in our testing data, we made this kind of error this often, and that kind of error results in $80 of therapy time, whereas the other error results in like 50 cents of annoyance. And you can multiply those numbers together, add them all up, and see how good your model is actually doing. In the real world, it's not always possible to do that, unfortunately. So what we have to do is come up with different error metrics that kind of get us close to that or get us some way of comparing models to each other. For regression problems, the common one is called mean squared error. I have an example here where we might have some true values that we know that we split out as part of our testing data, and then some values that I have drawn in green and with a little extra outline there in case you are colorblind. I don't know if you can tell as much up on the screen, but hopefully the ones with a stronger outline are the ones that are predicted values. And what you can do is subtract those numbers from each other and then square those and take the average. So then you can add up this last column here, divide by 4, and say the average mean squared error was 18.35 for this model. And that gives you some sense for how good or bad this model is that you can use to compare to other models that you might have. Another kind of error that you might, or another thing that people will often use is classification error, which is when you have some classification problem, you can just look at how many errors you're making. And so in this case, we see that we make one error. We accidentally classify a point that is truly orange as blue, and that means that we have roughly a 25% classification error. So these are metrics that we can use to quantify how good our models are. So at the end of each use case, we'll talk about some lessons that we learned. First thing is that it's pretty neat. It's just math, and computers are able to figure this stuff out, and you don't actually have to be a linear algebra genius to use this stuff and to get value from it. Another thing that we learned was very important is to have testing data so that way we can evaluate our models. Let's now move on to our next use case in which we will teach a computer sign language. So we'll start again, like all the use cases, with what is the problem. The problem is that I don't know sign language, but there's a lot of deaf people that I would love to communicate with because they have valuable things to communicate, and I think that's messed up that I can't communicate with them. So I found this little device that you can plug into your laptop, and it has a little like infrared camera and infrared LEDs and stuff in there. And in real life, you can't see this little violet thing that's coming out of here, but that's an IR LED. I don't know about photography, so I don't know why you can see it in the picture, but anyway, it shines IR on your hand, and as you're moving around your hand, it can sort of track where your individual joints are, something like this. So in this example, someone has the device on their desk, and they're holding up their hands something like this, and the computer is able to turn that into this three-dimensional data. So the data itself looks like this. We have 20 different points on the human hand, and it gives us X, Y, and Z coordinates for all 20 of those. Most of those are joints, but there's one in the middle of your palm, and I think there's one at the wrist or something. So what my friend and I did was we took this device, and we were at a hackathon, and we decided, let's try to do something to solve this sign language problem. So we plugged the thing into our laptop, and we said, we looked at the ASL alphabet, and we're like, let's just try the alphabet first. So plug it in, and we're like, okay, let's make an A above the sensor and like move it around and tell it, hey, this is an A, and just repeatedly told it an A, and then made a B above the sensor and hit B a bunch of times. And eventually we have this data set that you see on the screen where we have some points for each joint. We have X, Y, and Z points. And then we have a number of signs that we can try to predict. So our inputs are going to be these 60 points, these 60 data points, and then our output is going to be what sign is the person making, A through Z. Here's the best part. What kind of machine learning problem is this? Okay, clustering. Does anybody think it's anything different from clustering? Someone think it's classification? Okay. Anybody think it's anything other than clustering or classification? Okay, so it is a common, actually when I've given this talk before, sometimes people think this is clustering. It's not actually in this case, and the reason is that in clustering we don't know what we want to predict, but in classification we do. So in this case we do know that we want to predict an A through Z, and in this case so because you have 26 different things that you're trying to predict, it's a member of one of these 26 classes, it is a classification problem. So yeah, it's a classification problem, but not uncommon to think it's clustering. And clustering, you could do clustering on this. It just wouldn't be this exact problem that we were trying to solve. You might learn something else by doing clustering. So when we go into the solution part here, the first thing that we did was try to choose a model. We had this data, and we were trying to think what model is going to work well in it. So just like we've already learned, it's a good idea to split your data up into training data and testing data. And then we just imported every model we could from scikit-learn, and we said, let's just try a bunch of these things and evaluate them on the test data. Let's just train them and then run through and see which one does best. This actually is not the worst thing you could do. It's not like the greatest thing ever also, but it's as long as you're not doing this repeatedly over and over again, you could probably be okay doing this. You can run a risk of, if you do this over and over again, you end up picking a model that just does really well in your training data, but your real world data might not look like your training data, unfortunately, or might not look like your testing data, unfortunately. But this is not a bad first approach at this. And so then we thought, okay, cool, we got this amazing model. This is great. Let's build an application. The first thing we thought was, let's make a keyboard. Let's make it to where you can type in, letters A, B, whatever, and it will turn that into some text on a screen that you could use to type back and forth. Not that people can't type, but we just thought it was an interesting idea. Turned out this did not work very well. We were having a difficult time figuring out when are people changing the sign that they're making. And so we were like, well, let's just scrap that entirely and come up with something else. So we figured out that our model was still good enough that we can make a little educational game, kind of like a Rosetta Stone for sign language thing. And this is a little, let's see if this YouTube video wants to load. There's no sound on this or anything. But it shows you a little image of a letter and says, hey, make this sign. This is an A. This is a B, whatever. And then as you get it correct, it will give you points. And at the end, you get to type your name in as a little leaderboard, because I guess everyone loves leaderboards. Anyway, I'm not very good at this game. So this is just a little demo to give you an idea of what you can kind of do with this stuff. So there are some things that we learned in this process. And surprisingly, a large amount of things that I learned from this that are applicable today in my real world life that I didn't think I was going to learn from just this sort of 24-hour toy hackathon thing. The first thing is that defining the problem is really important and really challenging. Being able to figure out from this sensor, what data can I even gather from it? What is something that I find interesting? Kind of coming up with the intersection of that, and then coming up with, okay, what if we did sign language? Okay, well, actual sign language has its own grammar and its own rules, and there's a lot of, there are signs that move, for instance, and so you can't do something just based on a sound. There's so much complexity to this, but being able to come up with some problem that you can concretely solve and casting it as a machine learning problem is very difficult, and I think really important to be able to do. The thing that enabled us to make any progress was to limit scope. Again, I thought this was something we were just doing because we had a 24-hour hackathon. In real life, this ends up being super important too. When you have a problem that is large, oftentimes the best way to solve it is to break it up into smaller problems and then solve those individually. So in this case, we said, sign language is cool. And then we're like, okay, maybe just American Sign Language, maybe just the alphabet, which isn't super useful, but gets you a start at understanding what the kinds of problems that you run into are. We talked a little bit about model selection here. And this, for one, exposed me to the problem of model selection and how to figure out what model to use, and got me familiar with at least one method of doing that. Another really important sort of lesson that I learned was that it's more than just the model you have. You might have a model that will make you a garbage keyboard that doesn't work very well at all, but the model could still have value in being used for this Rosetta Stone-esque application, which is interesting. If you're working in a corporate context, this is a great place to sit with the product people and sit with your customers and try to understand what are their pain points and what are things that I can solve with machine learning to make their workload lighter or more efficient or whatever. Let's move now to forecasting energy load. So the problem here is that we have to know when to schedule energy production. Imagine that we are an electricity grid, and we need to know when to make our power plants start generating electricity, because I don't know, I'm not an engineer. Like, batteries aren't good, I guess, and so you have to schedule your energy production close to when it's going to be used, I think. This is not entirely hypothetical. So for any of you who are here from out of town, there's this thing in Texas called ERCOT, which is the Energy Reliability Council of Texas. And everywhere except, well, most places except notably Austin, have this deregulated energy market where people can buy energy from whoever they want. And I think what ends up happening is those providers turn back around and buy it from ERCOT or something. I don't know. Again, there's a lot of things I don't know, but this is a problem that someone has, and they have to figure out how to solve it. And you can see that they divide up the state into these different weather zones because, as it turns out, energy usage correlates highly with weather. So the data kind of looks like this. We have some time of the day and the hour, the date and the hour, and then the output. We have actually like 9 different outputs here. And you can download these Excel spreadsheets from ERCOT themselves, and they'll say, hey, this is how much power was used across the state or in each of these weather zones during this hour. So the input here we have is the time of day, and the output is the energy load being used in terms of kilowatt hours. I thought it was fun to put this on a little graph, so I did that. And even at this point, I think it's kind of interesting to look and see, well, in the summer, things get a lot heavier usage because it gets hot here and people don't like that. So even here, I think it's interesting, but we could apply machine learning to this, right? So what if we wanted to predict how much energy usage was happening? What kind of machine learning problem is this? Okay, regression. Does anyone think it's anything other than regression? Someone thinks clustering. Anybody think anything other than clustering? Okay, it is regression in this case. Good call. So, and the reason that it is regression and not clustering, again, is because with clustering we don't know the output. We're not sure what we're trying to output. In regression, we know that we're trying to predict the number of the amount of energy being used. So there's a strict number that we're trying to predict. And the reason that it's not clustering is because clustering we would be predicting like a distinct number of things, whereas with regression we're trying to predict a continuous value. So there's a number of things we need to know here with regression. The first is that when we're dealing with time series data, it often exhibits seasonality. This is a graph of weekly energy load across the state of Texas, and you can see that there's big bumps in the summer, and then sometimes you get these little bumps in the winter. If it's a particularly cold winter, people are going to run their heaters, but that doesn't happen super often here. And what's tricky is this thing that I told you was a good idea at the start of the talk, which is to randomly split your data up into training data and testing data, is not a good idea when you have time series data. And the reason that is because if you were to do that and have our blue data be the training data and our orange data be the testing data, we're going to leak some information. So if we look at this particular part of the graph, there's an orange point in there that is a testing data point. And it is surrounded on both sides by blue points, which means that those are points we know about, which means that if we are trying to test our model and say, hey, what would the energy usage be right here? The model can look ahead to the future and be like, well, the day after that, it's this. So I'm going to say it's a little bit less than that. And in real life, you don't know that. You don't know the future when you're making these predictions. So what you should do when you have time series data is do a split that's based on time, because that more accurately reflects the way that this model will end up getting used and the way that you will have information in production. So this is an example of sort of 6 different splits that you could make, starting with a little chunk, and then adding on some extra, basically taking a little extra in the future and saying, let's make our model predict for this. And you can do this a bunch of times and get a bunch of different splits between training data and test your model in each of those cases. Now, another tricky thing about time series data is that some models are not very good at it. So this is a model I trained, and it just like completely does a miss. It doesn't realize that it can do tricky things like this, and that is not great. So it's a good idea to do something a little bit more intense, and there's a lot of people who do a lot of research on how to model time series problems. And I would highly recommend using this library called Profit, because it will take a bunch of that research into account and make models that are a lot smarter than some others. So the main thing that we learned here is that time series data is really special, and you should think about it very carefully because it has seasonality. Don't use a random split of your training data and your testing data. The last thing we will talk about today is using machine learning to find our next job. So the problem here is passive job hunting, and this is a couple years ago at this point. I was reasonably happy in my job, but I was kind of like, maybe something cooler is out there. And I thought, well, this would be a fun little side project to do of gathering up a bunch of jobs and then figuring out which ones sound cool, and maybe I could like make a robot email me the coolest jobs. That sounds interesting. And so I made this thing, this little spreadsheet where I would go and enter in a bunch of jobs, and I would put a link to the job description. And then when I was bored, like I was in line at the, or like waiting for the bus, or like waiting for, at like Subway sandwiches or something, I'd pull up the thing, I'd click on the job description, I would go read it, I'd come back to the spreadsheet, and I would say whether or not that job sounded cool. Now, I will admit to you, just right now, no judgment, hopefully, that I spent way longer doing this than I would have spent like actually just using a normal like job search procedure. But given that all of you are at a software conference on a Saturday, I think this is a safe place for me to admit my over-engineering tendencies. So here we are at a question of what kind of machine learning problem is this? We have some information about a job, and we're trying to predict whether or not it would sound cool to me. I'm hearing classification. Does anybody think anything other? Okay, yes, this is a classification problem. The tricky thing here is we've seen data before where we're dealing with numbers, and we're trying to say from this number and this number, let's predict this value. But we have a job title now, and a job title isn't a number. So it's like, what do we even do here, right? Like, how do we turn a job title into the number 5? Like, what does that even mean? How would we do that? So I did what I highly recommend you do when you run into problems is Google just like, how do I do this thing? And so I Googled like text representations machine learning, and this is the first thing that came up. It is not a new idea, but it's a good place to start. So what you do is you take all of your documents, all of your job titles, and put them on the rows of a matrix, and then make columns for every unique word in the data set. So for instance, for this first one, we see that the word engineer does not occur in the job title, so we say 0, but the word web does, so we put a 1 in that column, and et cetera, et cetera. I'm not going to go through the tedium of filling this out for you because that sounds boring. One thing I do want to make sure you note is that in this model of text, if you have a repeated word, you can have multiple things. So if someone posted a job called data, 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 first of all, like, I'm interested in hearing about it. Second of all, you would get a 4 in the data column there. And what we call this is either word count vectors or a vector space model of language. So now we're able to take a job title and turn it into this word count vector. And we can take our sounds cool and encode it as a 1 if it sounds cool or a 0 if it doesn't. So now we have numbers, and we can plug it into scikit-learn again. And the code is actually relatively simple to do this. You can take these job titles, take whether or not it sounded cool, do this count vectorizer thing, which does the work of turning these titles into word count vectors, and then finally train a model on it. So we call fit, and that's going to do our work of drawing this fancy line, and then we can call predict on the new jobs that we have coming in and say, do these sound cool or not? And it will end up outputting this array that says, these ones didn't sound cool, but that 4th job did sound cool. So I did this, and I got a classification error of 20% about. And I'm thinking, this is great. Like, I'm barely even trying, and I'm already getting 80% accurate. This is awesome. And then I dug in a little bit further. And I found out that the base rate was 0.197, which means that only 20% of the jobs I ever found were cool. And my model figured out, I'm just going to say nothing is cool. And then I'm going to get 80% right. This is great. I'll get a B just for not doing anything. So I drew this self-portrait after I did that. The thing you should probably be doing is not just relying on classification error, because it can trick you in interesting ways. One way that people use to combat this is to use something called a confusion matrix, where you have the predicted values along one axis of a matrix and then along the other the actual values. If I had done this, I would very easily be able to see, oh, I'm just predicting 0 for everything, and all my errors are coming when there's actually these interesting jobs. And I would know, well, that's the only thing I care about, so clearly my model isn't doing well enough. Another set of error metrics you can use when you have this sort of imbalanced situation is to use precision and recall. To put it succinctly, precision is a way of asking, for all of the job titles that I say are cool, that my model says are cool, how many of them actually turn out to be cool? And then recall is a way of saying, of all of the job titles that I know about that are actually cool, how many of them is my model saying are cool? So if I had done this, if I had looked at this, I would see that my recall was 0 because I was not predicting that any title sounded cool. So 0 of the actually cool titles were coming back as cool. Another useful technique for imbalanced data is to do resampling of the data. So one thing you can do is take those 80% of jobs that didn't sound cool and just throw away a bunch of them because you don't need them, and you can get it closer to a balanced scenario, and your model won't be incentivized to cheat as much that way. If you make it balanced, it will realize like, well, I have to actually try now, is the idea. So I ended up doing undersampling, and then I made this little thing that would email me once a week. I've since turned this off, but it was a fun project. And it would email me once a week and say, hey, these jobs sounded cool this week. Go ahead and look at them. All right, there's some things we learned. The first thing we learned is understand what the base rate of your problem is. Try to figure out if your model is being silly, if it's trying to be tricky with you. You want to know that. You want to know what would happen if I did the dumbest thing imaginable and just predicted the most common class in each case. Another thing we learned is that a simple model isn't necessarily ineffective. I started this wanting to use some crazy deep learning stuff on text, and then I did logistic regression, which is a very simple model, and realized this works really well. How great. But I was also a little bit sad on the inside. And the reason this works is because of a thing called the approximation generalization trade-off. What that means is you can choose between being able to do really well at the training set or being able to generalize better to data that you haven't seen yet. To give an example that's more concrete, imagine we have these data points on the board that are our training data. And I have drawn the truth is this blue line, and then I have built two models, a linear regression model and a nearest neighbor model. The nearest neighbor model is incredible at approximating data. It actually has no errors on the training data. It is perfect at approximating. The linear regression model is not as good as approximating. There are places where it's kind of far from some of the training data. But what's neat is when we look at the testing data, the linear regression model, despite its lack of approximation, does a lot better on generalization. So when we choose simple models, we often are able to generalize better. And that's one reason why we should choose to use simple models at first especially, is because you get a lot of generalization ability just by using a simple model. The other thing is it's just easier. It's been a while since I've tried to set up TensorFlow or PyTorch or whatever on my laptop, but it is significantly harder than just pip install sklearn. So it's often easier to do this and faster to train, and you can iterate a lot more quickly when you use simple models. Okay. So I'll take a deep breath. We've talked about a lot of things. Some last takeaways to sort of try to tie a bow on this package. Supervised learning is a set of techniques where we try to use past examples to predict either a continuous variable in the case of regression or a discrete variable in the case of classification. You can measure performance of these models by splitting your data into training data and testing data before you do the training. Another thing we learned is to keep it simple. Because when we try the simplest thing that could possibly work, sometimes it works and you don't have to try the hard thing, which is very nice when that happens. And the last thing I will say is to test out your models and iterate. You are going to learn a lot more by trying out something that you can do very quickly, like a logistic regression model, and then figuring out what you need to do next rather than going through all the work of building some really complicated data pipeline and some really complicated model first, because using that simple model will then enable you to have much quicker feedback loops, which is really nice. All right, that's the stuff I have for you today. Again, I work at Indeed, and they are really nice for letting me come do this kind of thing. If you're interested in any of that, please come talk to me. The slides are available at this link here, go.indeed.com/PDA19. That's short for PyData Austin 19. I think we need to get moving to the next talk, so we don't have time for questions. But if you do have questions, feel free to email me. I would love to chat with you. Data stuff is one of my favorite kinds of stuff. So yeah, just email me. Would love to hear from you. And thank you for your time.
We can take 1 or 2 questions.
Oh, awesome.
Great. Hi. Thank you very much for great tutorial. Can we go back to the slides about the energy consumption prediction?
Let's do that. Yeah.
And the question I have is, I don't know much about energy consumption, but I would assume that it's not only time series problem, but also weather contributes significantly on how much energy is spent. So
Yes.
I was wondering what was the reason for you to include only the time-related.
Yeah, that's a great question. So the question, yeah. So he had a mic. I won't repeat it. The main reason for this is actually just for like pedagogical reasons. It's easier to just talk through like it's time. And the second thing is that you can actually get a decent model by using time because time and weather are so correlated. Now you can definitely have it be better by adding in weather data because there's going to be places where it's 80 degrees in December. Like that just happens sometimes. So yeah, that's the main reason is. But yeah, in real life you would definitely want to use weather in this case.
I was just wondering if you had an example of a clustering problem that you could share.
Yeah, so one thing that I think is, because I keep tricking y'all. I'm like, you think this is clustering? No, it's not. It's never clustering. So one thing that I have seen be interesting in clustering is if you think about like, let's use that, that jobs data set example. If we had some data set of jobs and let's say we end up having like 9,000 unique words in that, it might be computationally intractable to have a model that has 9,000 features. And so one thing that some people will do is cluster those job titles and try to find groups of job titles that are similar to each other. And then maybe you end up with like 9 groups. And then you can have, you can have like 9 features instead of 9,000. So some people, I have seen people use it as sort of like a way of understanding the underlying structure of the data and then using that to kind of build a model off of that instead of building it off of the raw data for some reason. Yeah. Another place I've seen it be used is if you're trying to understand your customer base, for instance, and you want to know who's buying our product, you can gather a bunch of data about them and then build some clustering over them and then analyze them and figure out like, oh, these are small businesses. These are large businesses trying to hire nurses, things like that. Yeah, and that can help you do a lot of things. Yeah.
Okay, thank you, Samuel.
Yeah, thank you. Appreciate it, y'all.